Hello, and welcome back to Introduction to Astronomy. And so now we are going to continue talking about some of the contributions that Sir Isaac Newton made to astronomy. Well, one of the other things that he did was he modified Kepler's third law. So if you remember, Kepler's third law was the one that said that the period squared was equal to the semi-major axis cubed. So that was the formula that Johannes Kepler came up with. Well, one of the things you notice is that in Kepler's version, or Newton's version, it has a G down in the bottom, which you would expect because that comes from his force of gravity, which has the big G. But then it also has the mass of both the object that is orbiting and the mass of the object that it's orbiting around. So when you add those two together, you get the total mass of the system. Now, for all intents and purposes, though, since the sun is 1,000,000 times larger than what the Earth is, so that means that really the total mass, when you add the mass of the sun plus the mass of the Earth, it's really just the mass of the sun because it's so much bigger than what the Earth is. So this M could be thought of as just the mass of the object that the thing is going around. If it's a terrestrial-sized planet that's going around the sun. And that makes the mathematics of it a little bit easier. So I wanted you just to see what is it that determines the period of a planet as it goes around a star. So according to Johannes Kepler, it's going to be the distance that it is from that star. But then according to Sir Isaac Newton, it's also going to depend on the mass of the star and to a much smaller extent, the mass of the planet. Another contribution that Sir Isaac Newton made to astronomy was that planets really don't go around their parent star. So everything I've been saying up to this point has been a fib, okay? Because what's really happening is that both the star and the planet are actually in orbit around each other. It's just that you don't notice it. So this gets into the idea of center of mass. And so to demonstrate this, all you got to do is get out a ruler. Get it? Okay, you got your ruler? Okay. So get out your ruler and then balance it on your finger, and you'll notice that it's basically in the middle of the ruler is where you can balance it. Okay, now what I want you to do is to get a coin and put the coin on the end of the ruler and now balance it. And did you notice that now you need to move the ruler a little bit so that it's in balance again? Well, where your finger is at really is at the center of mass. So when it was just the ruler by itself, the center of mass was in the center of the ruler. But when you put a mass on the end over here, you had to adjust it so that the center of mass moved closer to the quarter when you did that. So let's look at the first picture there. So the first picture shows a very massive object like the sun, and then a small planet that's in orbit around it. Well, it looks as though the planet is going around that star because the center of mass of that system is so close to the center of the star. So if you looked at it very, very carefully, you might notice that the star is doing this. It wobbles as the planet goes around. And we're going to find out that that's how we're going to locate other planets in our galaxy, is we'll look at a star and we'll look to see whether or not it's wobbling. And then the amount of wobble is going to tell us the mass of the planet that's in orbit around it. The more it wobbles, the bigger the mass must have been over here that's causing the wobble. Okay, the second picture shows a star, but this time it's like a Jupiter type planet. It's a much bigger planet, and so now you can see that the two of them are actually in orbit around their common center of mass. And then finally, the third picture is showing what would happen if you've got two objects that are about the same size. So this would be a binary star system. And in a binary star system, they're in orbit around each other like that, around their common center of mass. Now we could make this mathematical if we want to. So if you look up there at the top, you see equation 510. And so if you take a physics course, you would learn how to actually calculate where the center of mass is for a system. We're not going to do that, but if you want to look at that formula there and see if you can use it, then feel free to do so. Okay, in our next segment, we are then going to fast forward to the time of Sir Isaac Newton. Sorry about that, to the time of Albert Einstein. Okay, see you then.